record. All right. So first, let's just go over a little bit of what we talked about last time, and then we'll get into some of the new stuff. So briefly, what we talked about is the atmosphere has different layers. The one we care about is the troposphere, which is the one where most of the weather takes place, and it's where we're going to be flying aircraft. So that's one we care about. Inside the troposphere, we have our standard lapse rate, which is 2 degrees per 1,000 feet, and 1 inch of mercury per 1,000 feet for pressure. Inside the Earth's atmosphere, we also have atmospheric circulation, which is due to uneven heating of the Earth's surface, the Coriolis effect, and just the fact that as air rises, it wants to cool off and then sink back down, and that causes circulation within layers. And so you get different bands of circulation inside the Earth's surface, or just above the Earth's surface inside this troposphere layer, and you get this kind of rotating effect from that, which can cause differences in pressure and other things. So as far as pressure goes, we defined pressure, at least the standard of pressure is 29.92 inches of mercury at 15 degrees Celsius. And this is kind of like a baseline. This is what we call sea level. This is where normal is. Everything above it is high pressure and everything below is low pressure. This also correlates to 1013.2 millibars, which is a different expression of pressure. We talked a little bit about how altitude and pressure affects aircraft performance, but I'm not going to really go over that as much right now as we will when we get to aircraft performance. We talked a little bit about pressure. So pressure is, at least differences in pressure are created due to different heating of the Earth's surface. So different parts will heat faster than others. Unequal heating causes different parts to have different pressure than others. And this causes pockets of air, which are very large in scale. And these pockets have either a high or a low pressure, and air will flow from high to low pressure. Air flows outward and clockwise from a high pressure, and air flows inward towards a low pressure, rotating counterclockwise. We also talked a little bit about convective currents, which are local currents of air that are caused by like a lake being right next to land, in the case of like a land breeze. So you get different heating of the lake versus the land, which causes air to flow between them. You also have convective currents, around like parking lots and stuff, where a parking lot's going to be a lot hotter than a lake or even the ground next to it, and this can cause warm air to rise much faster there, and you can get turbulence and such events. We talked a little bit about wind, which I'm not sure if I mentioned this directly last time, but wind is caused by air flowing from high to low pressure. That's what causes wind. So wind, when it flows around the surface at least, or over like mountains and things, it gets kicked around and it creates turbulence behind those things like buildings or mountains or hills or whatever. And this turbulence can cause problems if it's severe enough. However, usually it's just something you have to keep in mind, that wind is going to swirl around at least near the ground. Once you get above it, 1,000 feet or 2,000 feet, this becomes less of a problem. But the wind on the ground is going to be a lot more different than it is up in the air. Talked a little about low-level wind shear and microbursts. We're not going to cover those too much right now. We'll come back to those eventually. We talked about how wind is represented on a chart, which you have a circle with, if there's no stick, it's calm. If it has a stick, it points in the direction of the wind. And each half barb is 5 knots and each pennant is 50 knots. And these are all located on charts around weather stations. So each airport that has a weather station will have one of these. Some airports, I guess, don't, but a lot of airports these days do. So that's how wind is represented. Pressure similarly is represented on weather charts, a different kind of weather chart, but it's represented by gray lines, which are lines of equal pressure. We call these pressure lines isobars. And these represent contours, kind of like an elevation chart, where all the pressure along that line is the same, and it's usually has the number on it next to it somewhere of what that pressure is. All right, so today, this is the new material now. We're going to talk a little bit about atmospheric stability, or maybe the lack thereof. In the last section, we kind of talked about pressure and winds, and in this section, we're mostly to be talking about moisture and clouds and air masses and stuff like that. So to start off, we're going to try and define atmospheric stability. And most commonly, when you see this term, what it's going to be referring to is really the resistance to motion of the atmosphere. So if an atmosphere is very stable, it's going to have little change due to certain things. So if something happens, if a front moves through, or there's a lot of convected heating, the atmosphere is not going to react to that as much, and the effect is just going to kind of be damped out over that area. If it's very unstable, then things can get out of hand very quickly. Things will grow. Clouds will grow very fast. There'll be a lot of turbulence. A lot of convective activity will turn into thunderstorms and the like. And unstable air is perfect breeding ground for thunderstorms and other types of severe weather. Typically, the cooler, drier air is the most stable. This brings good weather. It brings clear skies, much like if you're in Houghton right now. There's kind of cool. It's very clear. This is very stable air. It's not likely that a thunderstorm is going to pop up here. Conversely, moist, warm air is usually the least unstable. This is perfect conditions in like the summer for big thunderstorms. If you live like down in Florida, they have thunderstorms like every afternoon. It's very moist, warm air, and this leads to very unstable conditions, which in turn leads to thunderstorms. So this is something that you'll see a lot. Like we talked about before, the standard lapse rate being 2 degrees Celsius per 1,000 feet. Basically, all that means is that as you go up, temperature decreases, and this rate is known as the standard lapse rate. Now, there are exceptions to this, which we'll actually get to here in a few slides. But for what you need to know is because air cools as it goes up, this can cause certain things to happen when the air and humidity intersect perfectly. And this is kind of where we're going to get to talking about clouds and stuff. Just for reference, dry air and moist air have different lapse rates. The average is around 2 degrees, but dry air has lapse rate, around 3 degrees per 1,000 feet. And moist air can be anywhere from like 1 to 3 degrees per 1,000 feet, depending on how moist the air is. So lapse rates occur, that's the kind of like the normal. Now, there are exceptions to this, and the exception is a temperature inversion. Now, a temperature inversion, instead of air cooling off as you go up, what happens is the temperature actually increases as you go up. Now, this can cause a lot of different weather phenomenon, but most commonly it's associated with kind of hazy, kind of drizzly air that is, it just doesn't, it feels stagnant. And that's what it is. I mean, it traps a lot of stuff in that bubble that it creates, and this can lead to fog, haze, all kinds of stuff. So how these form is you can have, there's kind of 2 different ways that these form. So one is where at night, and it's like a clear night, so a lot of heat and stuff can escape the ground. And so the ground is going to cool very fast compared to warmer air above it. And so what you get is you get cool air near the ground and you get warm air above it. And this kind of creates this temperature inversion, which you would notice, obviously, once the sun comes up, because you're probably not awake at night. But and this temperature inversion will cause these types of things. It'll cause fog, haze, different things like that. The other type is a frontal temperature inversion, and we'll talk about fronts a little bit later. But Basically what happens is a front might intersect another front or another air mass, and this can cause warm air to go up over cool air, and that cool air kind of is pushed down towards the ground. You get warm air up on top, and so you get this gradient going from cold to hot, which is kind of reverse of normal. So temperature inversions are usually smooth in nature, and they have a defined cap region where the lapse rate returns to normal, and it starts to decrease as you go up instead of the other way around. So let's talk a little bit about moisture and temperature, because this is where we're going to get to the clouds. So inside the air, there is a amount of moisture that can be present in that body of air. Normally, we say that when the air reaches this maximum point, it's fully saturated and it can't hold any more air. Any more air will cause it, or any more water vapor would cause it to condensate out. Now, this amount increases for every 20 degrees, it doubles the amount of moisture that it can hold. So very cold air can hold very little water, and conversely, very warm air can hold a lot of water. And this is also why during the summer, you get more thunderstorms than you do in the winter, because there's a lot more moisture to build those thunderstorms. Now, water can enter the atmosphere in two ways. One is through evaporation. The other one is through sublimation. Evaporation is the more common of the two. However, it can sublimate out of things like sweat and other things. So that's how water gets into the atmosphere. Water can also leave the atmosphere through condensation and deposition. So when the air reaches its maximum saturation point, it's either going to condensate out, or it's going to do what's called deposition, which can take the form of like ice crystals just forming out of water vapor. That's much rarer, but it can happen. So relative humidity is how we define this relationship between the dew point and the temperature. So this area where the air is kind of at its maximum saturation point. The dew point is where the air literally can hold no more moisture. When you hear this term, usually it's an association with like fog or something, like the air is at its dew point, and so fog is starting to form at the ground, or frost, or something like that. Now, this dew point also is what allows clouds to form, and we can use some simple math to figure out where this is based on lapse rates and such. So if we wanted to figure out where a cloud base would form, where the air can hold no more moisture, all I have to do is apply this sort of simple formula to figure out where this cloud base would be. So in this example that they have, the temperature is 85 degrees Fahrenheit. Now, these numbers are adjusted for Fahrenheit. You can do this in Celsius too, but you have to get the exact ratios for it. But we're going to do it in Fahrenheit because we're Americans. And in fact, some weather products in the US are only in Celsius, so it might be helpful to know that too. Not that you'd ever really calculate this because it's very rare, but I do know they ask you these questions, or these type of questions, on the exam, so it's good to know. So air temperature is 85 degrees Fahrenheit. Dew point is going to be 71 degrees Fahrenheit. The convergence rate, which is calculated by taking the rate of cooling in unsaturated air, which in Fahrenheit is 5.4 degrees Fahrenheit per 1,000 feet. And then you subtract the dew point temperature decrease rate, which is 1 degree Fahrenheit for 1,000 feet, for whatever it's worth. And you get a convergence rate. So that's 4.4 degrees Fahrenheit. And we're going to apply that in our formula in the second step. So we're going to take our temperature, 85, and subtract our dew point. And this is going to get us our temperature dew point spread, the difference between our temperature and our dew point. Then we're going to take that number and we're going to divide it by our convergence rate, which will give us some value x. And that value x is what's going to tell us where the clouds can start to form. So you multiply that 1,000 feet and you'll get an approximate layer of where clouds will start to form. You can apply this, and usually it's fairly accurate. So there's something to know. They'll probably ask you questions on this. I've seen it, but after the initial test, you probably will never need this again. So, but that's how we calculate it in case you're curious. So how does air reach the saturation point? Obviously, you could add a lot of moisture into it, but more commonly, what happens is air masses move over each other, and this can cause temperatures to fluctuate, and this can cause the air to become oversaturated or undersaturated. So let's take the first example here. A warm air mass moves over a cool surface. So let's say a warm front moves over a cold body of water. Well, this cool body of water is going to start to transfer some of that to the warm air mass. And because the warm air mass is starting to cool down, some of the moisture has to be taken out of it in order for it to obey the laws of physics. So it takes some of that moisture out in the form of some type of precipitation or fog or something, and it loses that moisture so that it can cool down. It could also happen that a cool air mass and a warm air mass mix, temperature drops, and water has to precipitate out or somehow get out of that air. It can also happen when air cools at night, when the ground is cooler than the surrounding air, so the air is still warm from the day, the ground cools down, and this can cause air to condensate out. This can cause dew and frost and the like. And also when air moves up, because temperature decreases as you increase in height, the air has to cool down, and so water has to form in order for it to cool down. So like I said, when air cools down, it's going to form frost, dew, fog, clouds, some type of precipitation to get rid of that excess moisture. So let's talk about some of these types of condensation or how the water gets out of the air. So first we're going to talk about fog. Now there's 5 types of fog that we're going to talk about, and it's good to know what each of these is, because you'll probably get asked a question like, let's say at night air cools and the fog is formed or something. It'll be a little more complicated than that, but you'll have to know the answer to that question is radiation fog. So that's just like an example of how you might be tested on these. So let's talk about radiation fog. So radiation fog forms on calm, clear nights when there's little wind. The ground cools, and this ground cooling causes the air around it to start to form fog, especially if the temperature dew point spread is very close together. This happens very quickly. This happens a lot, in the spring and the fall when temperatures are increasing and decreasing. And you've probably seen this or run into this before. As soon as the sun comes out, it'll burn it off, and no problem. So that's radiation fog. Radiation fog happens at night when the ground radiates heat off of it. Terrestrial radiation is the term we give it. So radiation fog. Next, we'll talk about advection fog. So advection fog, unlike most types of fog, actually requires wind to form. So the wind pushes a layer of moist air over cool surface. So for instance, let's say you have a body of water. Now we'll talk about another one with a body of water, but let's just say this body of water, I don't know, is like a lake. So take Lake Superior, it's a cool surface. We have this warm air mass that's moving over it. And as this warm air mass moves over it, pushed by the wind, it's going to cool down and it's going to form fog. You might have run into this at the lake this summer if you were up here, or some other lakes where the lake is kind of cold still and a warm air mass comes up and goes over it, and the whole beach is covered in fog, but there's not really anywhere else. You go up from the shore a little ways and it's fine. You know that it's advection fog compared to like steam fog or something, because you can feel the wind. And normally when you feel wind, it's a little bit weird because fog and wind don't necessarily go together, but in this case they do. So That's advection fog. Let's talk about upslope fog next here. So upslope fog forms in like mountainous terrain, where there's like a valley and specifically mountains that are, you know, a little bit higher than like some of the ones that are called mountains around here, although some of them might be able to produce this. We're talking, you know, several thousand feet. So upslope fog also requires a breeze. And what it does is it pushes moist air up sloping terrain. So it pushes it up a mountain, and this causes the moist air to cool, and it forms fog. This type of fog usually is a lot harder to get rid of. It can last for days, and overall it's a little bit less likely to encounter when you're flying, but if you're flying mountainous terrain, a lot of this can happen. It doesn't burn off like other types of fog, so it's just something to keep in mind, but we don't really have anything around here that would necessarily cause upslope fog. So steam fog is a very common type of fog. You've probably seen it in the spring and the fall when water is kind of changing temperature from cold to warm or warm to cold, and the air is a lot warmer or colder than the water is. And so when you get this kind of temperature difference, when air moves over the water, specifically like cold, dry air moves over a warm water body, you get the water as it's starting to evaporate. It'll get cooled by this cool, dry air, and it'll form little columns of steam. I'm sure you've seen this type of fog too up here. It's pretty common, especially around like the portage and stuff. So the last type of fog is a pretty rare type of fog. It's called ice fog. This forms in very cold weather, and basically it forms when water vapor turns directly into ice. This is very rare. It has to be very cold, and it's unlikely that you'd ever encounter this in like a normal condition. I've heard of it a few times up here, I think, but yeah, it's very unlikely. It's very similar to radiation fog in the way it forms, though. So those are the main types of fog. Now we're going to talk a little bit about clouds. But before I go on, does anybody have any questions about anything we've covered so far? If not, then we will continue.
Sorry, right. I waited till the last second.
Oh, no, it's all good.
For these, for testing purposes, you said we don't need to pay attention to the mathematics. It's just going to be conceptual, correct?
So,
or are they going to ask us to calculate this cloud level?
Yeah, so they probably will ask you to calculate the cloud level. They'll ask you conceptual questions as well, but there'll probably be it depends. They change up the questions all the time, and the actual question bank isn't known. However, I know that in certain question banks this does show up. So yes, you might need to know this calculation. Maybe.
Okay.
Yeah, just for your own information. Yeah, you might need to know that.
All right, thank you.
Yep. All right, so let's talk about clouds. So clouds, like fog, are formed when water vapor condenses. Specifically, they form above the surface of the earth, and they form around some sort of nuclei, like dust particles, smoke, whatever. These clouds are all classified into different by different heights, by different shapes. Certain other characteristics, like say lenticular clouds, have a very specific way they form in a very specific shape. And they also have very specific characteristics, which is that they form around mountains and they have this kind of lens shape to them. But for all intensive purposes, we'll just call these three different types of clouds, and then we'll kind of get into different categories inside of that. So you have this base layer of clouds, which can sometimes include fog. However, usually we don't include fog in clouds. So We'll call these low clouds. They usually form from the surface up to 6,500 feet. And they're primarily just unfrozen water droplets. So it's just water. There's no frozen particulate matter in them usually. These can include like stratus clouds, stratocumulus clouds, nimbostratus clouds. These are low hanging clouds that aren't very, like, they're very close to the ground, and usually they kind of form this shelf. In fact, over the past few days, we've had a lot of these kind of low clouds that don't really move out of the area, and they just kind of hang around there, cover a lot of the sky. The next type is the middle clouds. Now, the middle clouds form from 6,500 to 20,000 feet, which is quite a range. So they can include water, they can include ice, they can include supercooled water droplets. Basically, it's a mix of ice and water, or some variation of that in case of supercooled water droplets. Some examples include altostratus and altocumulus clouds. These type of middle clouds you might encounter in a smaller plane. However, normally these are more things you'd start to worry about in higher performance turboprop and jet planes, especially for like icing concerns and stuff like that. And then the last category is high clouds. So these are clouds that form above 20,000 feet. For the most part, they're just frozen water, and they don't really pose any type of threat to pilots. So like cirrus clouds, cirrostratus clouds, and cirrocumulus clouds would all be categorized as high clouds. One specific type of cloud that kind of stands out from the rest is what's called a cumulonimbus cloud. I'm sure you've all heard of this. They're basically cumulus clouds, but they have extensive vertical development. They have a lot of instability inside of them, a lot of unstable air, a lot of moisture. These type of clouds usually start at the low to mid cloud range. They can start, 5,000 feet, 6,000 feet, whatever, and they go all the way up. They can go insanely high, a lot higher than you might think they can go. In fact, there's specific weather charts out there that just list the tops of these cumulus clouds or cumulonimbus clouds. And so in that's a large range of air. And so these have a lot of different weather phenomenon in them due to this. They can produce hail, wind, lightning, tornadoes. They're very dangerous, especially to pilots. Even to airliners, they're very dangerous, and they should be avoided if possible. Sometimes these types of clouds, cumulonimbus clouds, can be obscured in other types of clouds. So a system moves through, a low pressure system moves through, and it has a lot of stratus clouds, or it has a lot of other cumulus clouds. And sometimes these thunderstorm clouds can get obscured from view, and you can't see them until they're right on top of you, or if you have radar. And these are what we call embedded thunderstorms. So they're embedded within other types of clouds. They're very hazardous. They can have insane updrafts and downdrafts, sometimes up to 3,000 feet per minute, which in a small airplane especially, you're not going to be able to withstand that. Even in a moderately sized aircraft, you're probably not going to be able to, you won't have a good time. We'll just say that. So that's cumulonimbus clouds. Some other types of cloud classification, cumulus, like we talked about, is heaped or piled clouds, and these can grow into cumulonimbus clouds. They're the fluffy clouds that you see out there on like summer days when it's hot. They can vect up and they form these little puff balls. Stratus clouds, they're low to the ground. They form layers. They, they hang. It's very dreary. I'm sure you've seen these types too. Cirrus, they're high clouds. They're mostly made of ice. They're very thin, wispy, and there's not much to them. So Castellanellus clouds, I don't know. I've actually never heard of these type of clouds before until I put this presentation together. Apparently they're castle-like. I guess they're kind of like cumulus clouds that kind of form together, and they have like separate spires at the edge. I'm not quite sure. I've never seen one of these clouds. Lenticular clouds are lens-shaped clouds. So these clouds form specifically in mountain regions. So behind a mountain, you'll get these types of clouds that are like lens shaped, and they form in the currents behind the mountain. And I've actually heard stories of people who take their gliders out, and you can park your glider going down towards the ground in one of these lenticular clouds, and the updrafts are so strong in them that you can just sit there and just kind of surf the waves coming off the mountain. Um, some people describe these clouds as kind of like UFO clouds because they're very circular, and they can form when like there's nothing else around them. So they're very cool. I doubt you'd be able to see one around here though. So nimbus clouds. These are all rain-bearing clouds. So they don't have to be cumulonimbus clouds. There are other type of nimbus clouds, but any cloud that rains is going to be classified as a nimbus cloud. You could have a stratus nimbus cloud, for instance, or a nimbostratus. Fracto clouds. These are kind of broken clouds that don't really have a lot of form to them. I've never heard a cloud classified as a fracto cloud before, but I'm sure they are. And then alto clouds. So these are the middle level clouds. Just kind of, it's slapped on everything in that range. They're kind of up there, but they're not like high like cirrus clouds. So that's kind of clouds, fog. We'll get into precipitation a little bit, but so far we've covered the two types of ways that when water condenses, it forms in the air. So one of the major things that we have to consider when we're flying, at least when we're VFR, is where our ceiling is. Now, the definition of a ceiling, and this is, again, one of those things that you'll probably want to know because I'm sure they'll ask you a question on the definition of a ceiling, is, this is the definition: the lowest layer of clouds that are reported to being broken or overcast, or the vertical visibility into an obscuration like fog or haze. So what does this mean? First, I guess let's just describe what broken or overcast means. So in the weather world, when they're measuring the ceiling, they have normally some sort of, they don't do this by human vision anymore. They usually have some sort of laser thing that shoots beams up into the sky and gets where clouds are and where clouds aren't. But basically they, like this picture shows, they divide the sky into eighths. Why eighths? I don't know, but they divide it into eighths. And so what they do is they count how many eighths are covered by clouds. If it's more than 5/8 cloud coverage, that's considered broken. And obviously 1/8 would be fully overcast. There's also like scattered, which I think is like 2/8 or something to 5/8. I'm not quite sure. I don't remember exactly. But what you need to know is broken is 5/8 to 7/8 cloud coverage, and overcast is full 8/8 cloud coverage. And this is how we define the ceiling. Now, what does this mean for VFR pilots specifically? That is, pilots that aren't flying by their instruments alone. Well, you have to remain a certain distance below that ceiling of clouds, if there is one, and you have to maintain a certain distance from clouds in general. We'll get to that more in the Federal Aviation Regulations section, but for what you need to know is that at a basic level, you need a few thousand feet in order to fly. So this ceiling definition will help you out when you're making that decision. The other thing that is important to know when you're flying, especially VFR, is the visibility. So the definition of visibility is the greatest horizontal distance at which prominent objects can be viewed with the naked eye. This is kind of a subjective definition. So like ceiling, it's also been automated these days. So weather stations automatically get visibility information based on sensors and such. So there's a little that humans do. In fact, inside METAR reports, if a human writes that report and they get the visibility themselves, it's stated at the end of the METAR report that that was human observed instead of machine observed. So the visibility has an impact on how we classify whether it's VFR or otherwise. Just like ceiling, that also goes into effect here. So A VFR classification of visibility is anything greater than 5 miles. Now, most weather stations will not report anything greater than 10 miles. So if you see a number between 5 and 10, we just assume that's what we call VFR, visual flight rules. The next category is what we call marginal VFR. Now, these are the basic minimums that you have to have in order to fly VFR. And let me tell you, 3 miles is not a lot. You might think 3 miles is a lot on the ground, but 3 miles in the air is it's not a very large distance, especially when you're going, a few hundred knots over the ground. You cover that distance pretty quick. So 3 to 5 miles is what we call marginal VFR. Anything below 3 miles is not considered VFR, unless you're flying under special regulations that allow you to do that. So below VFR is what we call IFR. This is instrument flight rules. This is for pilots and aircraft that are capable of flying on their instruments alone. 1 to 3 miles, they're not looking outside at all. The idea is that you're flying solely based on navigational equipment and based on your instruments alone. And then below IFR, that is below a mile, you get what's called low IFR. These are, depending on the field, you might not even be able to fly in there. You might not be able to shoot an approach. Some approaches might have minimums that are above a mile, but this is, reserved for very hazardous conditions at airports. All right, so let's talk about precipitation now. So there's a lot of different types of precipitation. There's a lot of crossover and gray area between types of precipitation. I don't think that anyone's expecting you to know all of these. In fact, I had to look up what half of these were because I had no idea what they were. So really what you need to know is, rain, hail, rain, snow, hail, maybe like snow pellets or something. But other than that, you really don't need to know all of these or the definitions. But we'll go through them just because we're talking about weather. So rain, that's liquid water. It's greater than 0.02 inches in diameter. It's just, classic rain. Drizzle. This is liquid water that has a diameter less than 0.02 inches. Not sure how they measure this, but they have ways of doing that. It's just smaller rain. Snow. This is what is all familiar to us. These are ice crystals that are formed directly from water vapor in the atmosphere, and then they precipitate down. Hail is liquid water that has become frozen. Typically, you find this in thunderstorms where you have liquid water at the bottom where it's warmer, and as it makes its way up through the thunderstorm up to 20,000 feet or whatever, it cools down and it freezes. And hail then comes back down because it's heavier, and updrafts can't keep it up there any longer, and it falls back down. And as it falls, it melts. Sometimes this process repeats, 20, 30, 40 times or whatever. And this is how you get very large hail, depending on how large of an updraft there is. The cycle of melting and freezing and melting and freezing. In fact, if you look at large hailstones, you'll see these bands where it freezes and melts and freezes and melts. And then eventually, when the updrafts can no longer support it or the thunderstorm dissipates, they fall to the ground as hail. Hail is classified as anything greater than 1/4 inch or greater in diameter. Anything less than that is what we consider a snow pellet, which is the next item. So snow pellets are basically just hail that is less than 1/4 inch diameter. They're very small. Sometimes you'll get them with very minor thunderstorms, depending on the conditions. Ice pellets are similar to hail and snow pellets, but these are frozen raindrops, so they might form a little bit differently than, say, hail, which is kind of frozen on the way up. These might be frozen like on the way down. It just depends on the conditions. Usually the outside's frozen, the inside might not be frozen, whereas hail is probably going to be frozen all throughout. These they might have a soft core, depending on if it's cold enough or not. Usually they have a diameter about 1/5 inch or less in diameter. Snow grains are basically frozen drizzle. So these are very small drops of water. that are frozen, and they fall to the ground. I don't know that I've ever experienced snow grains, but they exist. Ice crystals. These are a very unique type of precipitation. They're kind of rare, I guess. They are basically falling crystals of ice. Now, these aren't snow crystals. Um, they are different type of ice crystal. Sometimes they form like hexagons, or they form long spikes. It just depends on the conditions. It's what we call diamond dust. And a lot of times they'll look like fog. They're not very big. They're very small crystals. And sometimes, I don't know if you've ever heard of a light pillar, but these diamond dust crystals, when they fall in certain things like populated cities, all the lights from the city get reflected off of these crystals, and you get these huge light beams that form from the light reflecting off of all these crystals. And it's pretty cool, actually. You should look it up later if you haven't ever heard of it. There's pretty cool pictures out there. And then last type is what we call unknown precipitation. These are only automated stations. So like Houghton's, for instance, has an automated station, and sometimes it doesn't know what's happening. And so it reports unknown precipitation. The last time I saw this was, I think last year, the year before, when we had that huge snowstorm come through. It was really cold and really windy. And the METAR reported unknown precipitation several times because it was basically snowing upwards. At that point, it was pretty bad. Now, you might have noticed the little parentheses with the abbreviations in them. Now, do you need to know all these? No. However, when we get to reading METARs and weather reports, you might need to know some of the basic ones. So rain, snow, hail, those types of things, drizzle. You'll need to know those for reading weather reports. The other ones, it doesn't really matter. You can go look those up at any time. So just know the basic ones so that when we start to learn how to read METARs and weather reports, it'll be a little bit faster. All right, so that was our section on kind of like atmospheric stability / moisture, clouds, fog. So we're going to kind of start moving on to beyond that. But before I do, does anybody have any questions about anything we've covered in the last little bit?
Is it common to fly in hail at all, or is that something that's like completely avoided?
Yeah, so we try and avoid that. In fact, there is a federal aviation regulation that says we're supposed to stay 50 miles away from thunderstorms, regardless of aircraft type. And so that's probably the only place you'd be experiencing hail. So yeah, it's pretty uncommon.
Okay, cool.
Yeah. Yep.
Is there a good reason why they're using G's for hail and stuff? Like in the abbreviation? Why is it GR for hail?
Right. So some of these abbreviations, now I'm not sure specifically about hail. I'd have to look it up, but I know some of these abbreviations come from other languages. So probably has to do with hail being called something else in a different language. I'm not quite sure, but I do know that some of these come from other languages.
I feel like I remember hail ice being called glass in French. That might be it.
Yes, a lot of these terms do come from French, so that's possible. That's actually probably likely, but I'd have to look it up to be sure. But yeah, that's my understanding of it. All right. Well, if there's nothing else, then we'll get started on air masses here. So, air masses. These are kind of the main drivers of weather patterns. Besides, obviously, high and low pressure. However, those are intertwined with these. And hopefully, as we get through these, everything will kind of start to make sense and kind of fall into place. So, air masses are big. They are large bodies of air that are similar in characteristics. So, like this image shows, we have like a cool, humid air, we have warm, humid air, hot, dry air, cool, dry air. And these are the four basic types of air masses, and they all form in different types of regions. So warm, humid air forms in the Gulf. Cool, dry air forms in polar regions. Cool, humid air forms in kind of higher latitude regions off the coast usually. And then you got kind of interior air, which is usually drier. And so these large bodies of air will then move around once they get pushed by different things, heating and high, low pressures and stuff. So the basic formation of them, though, is that when air kind of sits around a region for a while, it kind of takes on its characteristics and it forms these air masses. So when these air masses meet, we get what's known as a front. So each of these air masses, where they intersect with one another, they form front lines. And this is kind of what you'll hear about in the news. Like, let's say, there's a big thunderstorm coming through and they say, oh, it's some sort of cold front squall line or something. And what that means is that you have a cold air mass that's pushing through the region, and it's causing some disturbances and creating thunderstorms and stuff. And we'll talk about that here. So fronts basically bring weather changes. So behind the front is a different air mass, and with that air mass comes different weather conditions. So whether it be a warm front or a cold front or another type of front, whenever a front moves through, the weather is going to change behind it based on whatever air mass is behind it. So there's four main types of fronts that we're going to talk about. One is a warm front, the other a cold front, and we have stationary and occluded fronts. The other thing you should know is that fronts are also the boundaries between areas of high pressure. So if you want to think about it this way, high pressure is kind of like the top. So everything flows outward from a high pressure system like we talked about before. And so what you can deduce from that is that high pressures are the centers of air masses. So everything kind of flows out and away from a center of an air mass. And so high pressures are kind of the center of these air masses. And so two air masses are going to have two different high pressure systems. And so the boundary between them, a front, is kind of like this area where high pressures meet. Now that's kind of a general thought. I wouldn't take anything too crazy from that. But so when you have two high pressure systems around each other, like we showed in the other slide, low pressures and high pressures rotate so that they kind of match each other. So high pressure rotates into a low pressure. But when you have two high pressures next to each other, the air rotates in similar ways and clashes. And so what you should know is that when high pressure systems move around each other, especially when fronts move through, wind shifts are common, and the wind direction will probably change behind the frontal system because the high pressures rotate in the same direction. So warm fronts. Warm fronts are obviously warm air masses. They're a lot slower than cold air masses. They usually move about 10 to 25 miles an hour, depending on the conditions. They're kind of like the gentle giants of fronts. Usually they don't have a lot of crazy weather. Sometimes they might have like some rain or something, but usually they don't develop like insanely strong thunderstorms like cold fronts do. When a warm front passes, the slope of the front is going to go up over the top of the colder air it's replacing. And we'll look at an image on the next slide here about how this happens. But so the warm front will come through and it will move up and over a cold front. And as it gets lifted, the warm air obviously cannot hold as much moisture because it's cooling down. And so water starts to precipitate out of it, usually in the form of rain or fog or whatever. And it starts to rain at the boundary between a warm and a cold front. There are possibilities, depending on instability, that thunderstorms could develop around a warm front. However, this is pretty unlikely. So some common weather, there's rain, sleet, drizzle, sometimes poor visibility around warm fronts. Because they don't move very fast, usually there's not a ton of severe weather. Another thing you could note is that Barometric pressure usually will drop before the passage, and then it'll kind of settle, and then it'll drop again after the passage. So this is what a warm front looks like. So you can see the warm air is moving to the right of the picture, and it's going over this cold air. And as it moves up over this cold air, it starts to precipitate out as it cools down. And out in front of it, you'll see that the cirrus clouds kind of start to form, and then it goes lower and lower and lower. And then eventually, as the front hits you, you start to get these bigger clouds like nimbostratus and stuff, these lower hanging clouds. And so on a weather chart, just for your information, I know on aviationweather.gov, though, they tell you this, it's always usually, unless it's a black and white chart, it's going to be a red, and it's going to have these kind of half circles on it. And this is how they represent a warm front on weather charts. So it's this red line with half circles. They'll always have half circles. Whether or not they're red depends on the chart. But half circles, red line is a warm front. And we haven't learned to read METARs yet, but I'll kind of go over what these weather reports are on the bottom. So as this warm front approaches, you can kind of see that rain starts to form. That's the -RA on the side. That's rain. So as it approaches, you're going to get some light rain. And eventually, as you get further out, so like Columbus here, it's just hazy here. But eventually, it's going to turn from haze to rain as this warm front passes over it. The next type is a cold front. So a cold front, these are the stereotype thunderstorm makers, is a cold, dense, stable air mass that's moving and replacing a warm body of air. Usually they're pretty fast. They move about 25 to 30 miles an hour. They could be as fast as 60 miles an hour. That's pretty rare. They usually stay close to the ground, and they push that warm air mass out of the way as they slide underneath of it. So as they move very quickly through the area, pushing this warm air mass up, kind of like a plow, the warm air moves up, it has to cool down, and that means that water has to precipitate out, and it forms big clouds, usually thunderstorms, sometimes not, but usually it forms some sort of cumulus or thunderstorm cloud, and you get some pretty crazy storms with it. Cold fronts usually create much more severe weather than other types of fronts, just based on the fact that they move much faster than other types of fronts. And so stuff doesn't have a lot of time to get out of the way, and it's just forced up, especially if there's a lot of instability. You get some pretty strong thunderstorms from them. One thing to know is that pressure will decrease pretty rapidly when the storm approaches, and then it'll just slowly increase after the passage of the cold front. So here's a picture of a cold front. You can see on the left there, it's moving in to replace the warm air. And as it does that, it has to force the warm air up, and it causes big cumulonimbus clouds to form and precipitate at that front boundary. And if this storm is fast enough, you get what's called squall lines, which are very low to the ground, and it moves through very quickly. You get these huge cells of storms along that frontal boundary. If it's a little bit slower, the storms will be a little more spread out. And if it's really slow, then it might even be just rain that comes from it. But usually during the passage of a cold front, there is some type of precipitation. So the next type is a stationary front. Stationary fronts occur when you have two air masses that really are about the same strength. So when one meets the other, they can't push each other out of the way, and you just kind of get this stalemate. They usually persist sometimes for days, weeks, until one air mass pushes the other out of the way, and then it continues on. Usually it produces some sort of drizzly weather, low clouds, just kind of gloomy, and there's not a lot going on as far as the weather is concerned. This pattern just persists for days. Eventually one will win, and it'll move out of the area, but these are not the most exciting of fronts. The next type is an occluded front. Now, an occluded front occurs when you have a fast-moving cold front, and it catches up to a slower-moving warm front. So this is when a cold front overtakes a warm front from behind. So during the passage of an occluded front, warmer types of weather will usually hang around until the cold front moves over that warmer air mass and overtakes it. Then it'll transition to very cool weather very quickly. There are actually two different types of occluded fronts. There's one which is called a cold front occlusion. This is what happens when a cold front is colder than the air in front of it. So in between the cold front that's behind the warm front, and then in front of the warm front, there's usually going to be a colder air mass. Now, this air mass usually has a cooler temperature or a warmer temperature than the one that's overtaking the warm front. So what you get is a cold air mass overtaking a warm air mass with a cool air mass in front of it. And what happens is this cold air wants to move in to replace the cool air that's in front of it. And what happens is the warm air is forced up and out of the way. So a lot like a cold front, that warm air is forced up into the atmosphere, and you get some type of precipitation or thunderstorm clouds, depending on the instability, based on the fact that warm air is moving up and it can't hold as much water when it cools down. The other type is a warm front occlusion, and this happens when air in front of the warm front is actually colder than the air that is overtaking it. And so what happens is the cold front will actually go up over the warm front, and if it's unstable enough, it can produce very severe thunderstorms, even more severe than cold fronts. And that cold front will overtake the warm front, go up over it, and then into the air in front of it. During the passage of an occluded front, usually you get rain, heavy precipitation, sometimes very severe weather depending on instability. And usually the pressure will drop prior to the passage, and then it'll just level off before it drops again after the passage. So this is what a warm front looks like, an occluded front. So you have a cold air mass, you have a cool air mass in front of it. And so the cold air mass moves right across the screen here, and it catches up and it goes into the cooler air mass, and it forces warm air up into the atmosphere, creating cumulonimbus clouds and nimbostratus clouds and other rain clouds. And then out in front of it, you kind of get these cirrus high clouds and altostratus clouds moving in towards it. I guess I didn't mention this last slide. Cold fronts are represented by a blue line with triangles. And the occluded front is represented by this kind of mix. So you get a warm front, cold front sign, and then a warm front, cold front sign. This pattern repeats. So you get a half circle, triangle, half circle, triangle. Sometimes they're purple, sometimes they're not. Just depends on the weather product. And then you just kind of get this pattern, and usually they don't last very long in the chain. Usually you get about maybe 5 to 10 of these little things, and then it turns back into a cold or a warm front. So they usually are centered around areas of low pressure, where these cold fronts catch up to warm fronts. And also stationary fronts are like occluded fronts, except the triangles and half circles are pointed in opposite directions. So yeah, those are types of fronts. Real quick before we finish though, I'm going to show you a weather map, and we're going to look at what these things look like right now. Oops. We're going to share a different screen. All right, so let's take a look at what these things look like on a weather chart real quick. So this is the current weather map of the United States. This is on aviationweather.gov. Up here, you can see in the middle, we have this cold front line. And up here near this low pressure system, we actually have an occluded front, this purple region where you have this triangle and a half circle. So this cold front has caught up to this warm front right here, and it's created an occluded front. And actually down here, we also have a legend in case you ever forget. So we're just looking at a few days out here. Okay, this is interesting. So we have basically every type of front on this map. So up here, we have a stationary front. So this warm front that's pushing up this way has met a cold front, and according to the weather models, it can't break it. And so it's just going to sit here until it moves out of the area or one of the fronts breaks. Along this area of low pressure here, you can see an occluded front where this cold front here has kept up and caught up to a warm front. And it's created that occluded boundary there. Let's see, we have a cold front here along the boundary, warm front. I don't know if we have any straight. Oh yeah, down here in Florida, we have a straight warm front. So that's pushing up from the Gulf up into Florida. And then it's kind of being hit by a cold front over on the right side. Push a few more days. So here's something interesting. Looks like on Wednesday, actually this is going to be Thursday night because it's a zeros, or Tuesday night. So it looks like Tuesday night, we're going to have a low pressure system moving through with an occluded front. And this is going to cause some rain to happen on Wednesday. So that's some aviation weather knowledge you can put into practice right there. Occluded front moving through on Wednesday, going to cause some rainy weather. So that's just a quick look at weather charts. We'll look more in depth at these, but I just wanted to show you what those look like on a real weather product. Before we end, does anybody have any questions about fronts or anything like that? Or anything in general that we covered today? All right. Well, if not, I will